reading this equation. So the equation is Q equals mc delta T. This is the equation we used in the Cheeto lab. Okay? So Q stands for heat, obviously. C is specific heat. Again, totally makes sense. M is mass. Delta T is change in temperature. So we've actually solved these problems before already. You had to use this to solve for the Cheeto lab. So I'm not going to belabor the point. I'm not going to spend more time on it. I'm going to leave those for you guys to work on later in the period. So let's go ahead and jump down to the two new things, and that is the internal energy equation and then the first law of thermodynamics. So first of all, in the internal energy equation, so really it's delta U, so put the delta in front just so it doesn't confuse you. That's change in internal energy. Okay? So delta U, change in internal energy. N is the amount of the substance. So how much stuff you have. And R is the gas constant, which works for other things than just gases. But the value is 8.314. That's good. Let me get you the practice we're working on here. You'll have to finish the notes, but they're all on Schoology and those discussions we did, so you can finish those on your own later. Okay. So I want you guys to see if you can do 3 now. So what happens to the temperature of an object if its internal energy decreases? So here's the equation. Delta U, that's the change in internal energy. So if the internal energy goes down, so delta U gets smaller, what's going to happen to the temperature? Take 30 seconds, see if you can figure out an answer. I'll give you a hint. The answer is either it'll get bigger, it'll get smaller, or it'll stay the same. So what do you think is going to happen to the temperature? Bigger, smaller, or stay the same? Temperature, less temperature, or stay the same for the temperature? What do you think? You are correct. It is going to be less. You'll notice that N is a constant. It's how much stuff there is. That's not going to change. R is a constant. It's 8.314. That's not going to change. 3/2 is a constant. It's 3/2. That's not going to change. The only thing that can change is delta T. So if this number gets smaller, delta T has to get smaller. That's why it happens. So if you lose internal energy, your temperature goes down, which makes sense. The energy leaves and your internal energy gets lower. If you go outside without a coat in the winter and it's cold outside, your internal energy goes down. And that's because you're giving off heat to the cold air around you. Good. All right. First law of thermodynamics. So first of all, delta U is still change in internal energy, so I'm not going to write that one again. Q is still heat, so I'm not going to write that one again. W is work. Yeah, change in internal energy. Yep. Okay. So, an ideal gas expands without changing the temperature. It does 3.4 times 10 to the 3rd joules of work in the process. By how much does the internal energy change, and how much heat is absorbed? So see what you can do on 4. So how much does the internal energy change by? It doesn't. Now, if you didn't get that, look at this equation up here. No change in temperature. So it expands without changing temperature. Delta T does not change. That means delta U doesn't change. That means there's 0 change in internal energy. So, Jess, how much work must be done then?
3.4 times 10 to the 3rd.
Yep. Or how much heat, I guess I should say heat is done. 3.4 times 10 to the 3rd. And if you wonder where we got that from, Q equals 0 plus 3.4 times 10 to the 3rd. Ignore the 0 because 0 is 0, and you get Q equals 3.14. Okay? So in this case, the heat isn't changing the object's temperature. It's not changing its energy. The heat is doing work. Okay? And that happens. You can use heat to do work on objects. Okay? Think about a combustion engine. Okay? It's using heat to do work on your engine motor. All right, number 5. In a car engine, an ideal gas is compressed without gaining or losing any heat to half its volume. In doing so, 1,850 joules of work is done on the gas. A wants to know what's the change in internal energy. B wants to know will its temperature increase, decrease, and why. So go ahead and answer 5 for me. All right, so what do we think? What's the change in internal energy going to be? Jared, what do you think?
Well, it's being compressed, so my first thought was less, but is it not going to change since it's not gaining or losing?
So it's not gaining or losing heat, but it doesn't say it's not gaining or losing temperature. So it is going to be something, okay? So it is going to be something. How much do you think it's going to be?
Probably.
So you thought it was less than...
Yeah, less.
So you thought it was less than the 1850?
Yeah.
Okay. You're right that it is going to be related to the 815s or 1850. So let's look. So no heat. So Q equals delta U plus W. So Q is 0. And the work is 1850. So if there's no heat, then delta U is going to be the same thing. So it's actually going to be equal. Sorry, not Newton's joules. Too busy doing forces in Physics 1. Yep. Yeah, so let's talk about the directions here. The directions are complicated, so I'm not going to be too picky on them. If you say negative, I'm okay with that. Technically, W is negative in this problem. Work done on stuff is negative. Work done by stuff is positive. So think of it this way. If I'm doing the work, I feel good about myself, so I'm positive. I know it's cheesy. Okay? If someone does work on me, I don't like that. I don't like when people make me do work, okay, when they do work on me, so I'm negative about that. That's how I remember it. It's really corny and cheesy. I apologize. But that helps you remember it. That being said, I'm not going to be particularly particular about the signs for this particular problem. That's way too many particulars. Okay? So will its temperature increase or decrease? Hayden, what do you think? Increase or decrease? Yeah, so it should go down because, again, this should be, or sorry, technically this would be a negative. You would add it over. I just want to know that the temperature is going to change. As long as you can explain the temperature is going to change, whether you say increase or decrease, I'm not going to be too picky on. It is going to change. So will the temperature change? So it will change. Yeah, well, I'm making it easier for you. Don't make this worse than it needs to be. I'm making it easier by not worrying about the signs. Yeah, so the reason why is because the internal energy is going to change. If delta U changes, delta T has to change. So the temperature is going to change because the internal energy changes. And the reason why those are related is KE equals 1/2 mv squared equals 3/2 KT. That's the equation we did a little while ago. And don't worry, we'll review all these. But the internal energy is the kinetic energy of the particles. If you make the kinetic energy of the particles higher, you're going to make the temperature of the whole thing higher as well. Okay? So, here's what you have to do the last 10 minutes. So you got plenty of time to do it, knock it out, and be done. 1 and 2. Okay? 1 and 2 are using the Cheeto Lab equation, the Q equals mc delta T. Figure out what goes where, plug the numbers in, and solve. This is the one example where Celsius is the correct temperature. Okay? You actually don't want Kelvin on this one equation only. You'll notice I did not bold Celsius. That's how you know not to convert it. Yes?
Is the specific heat of water 4.186 or is it 4,186?
Yeah, because in one of the things.
So it's 4,186. The 4.186. Oh no, I think you might be right. Let me check my lab. No, I think I might have missed it.
Because in chemistry it was like 4.1.
Yeah, I want to say I had a typo on that. Because I know I wrote it in the lab. Yeah, it's 4.186. Thank you. Oh, but actually, I think I know why. Yeah, it is 4,000 because mine's in kilograms, not grams.
Oh.
That's why.
Okay. So it's
Yeah, I did make a mistake. That's kind of nice.
you made a mistake.
No, I didn't.